Good afternoon, everyone. Today, we have the privilege to hear from Professor Asita Emami. He is the Andrew and Peggy Kern Professor of Electrical Engineering and Medical Engineering, and she holds several hats at Caltech. Emami works on, works on so many areas, low power mixed signal circuits, and also optoelectronics and etc. And today, she's going to give a talk on electronic and photonic co-design for high-speed data communication and beyond. Thank you so much, Asita, for accepting, for giving this talk. And the floor is yours.
Thank you so much, Ajay, for the kind introduction and for having me today. Hi, everyone. Thanks for joining us. As Ajay mentioned, today I would like to talk to you about co-design of electronics and photonics for high-speed data communication, mainly on the transmitter side today. And then if there is time, I also talk about electronic photonic co-design for biosensing applications. As you all know, data centers today are very, very large and very, very complex. If you look at, for instance, this one example of Apple's Mesa data center in Arizona, it has a huge footprint with huge amount of investment that they continuously actually expand these data centers. And they try to make them highly energy efficient and also highly green with about 50 megawatts of solar power plant for this particular one. However, these data centers mostly are not 100% green yet. If you look inside the data center, you see huge number of cabinets and racks of servers and computing devices that are connected to each other at varying distances. So this is again inside the data center. We have communications between the racks, even within the board, between cabinets, and across the data center. In addition to traditional applications of high-performance computing and data centers, now we have the additional applications of generative AI and IoT devices that require significant data communication and networking. In fact, as you can see here, there is a huge growth for generative AI and AI servers within data centers. And the percentage of AI servers versus general servers are increasing rapidly, and they need very fast networking systems to support the communication between the servers and beyond. So on average, when we look at the data rate, data communication across all different standards, we see that the data rates need to approximately double every 4 years. And this trend, in addition to increasing the number of servers, means exponential growth of energy consumption in data centers, not only by servers, but also by the communication systems in the servers. So power consumption is extremely important. And now combine this with the fact that we need higher data rates per lane, and we need to cover longer distances. So the problem becomes extremely difficult for communication using cables and wires, while they are more cost efficient and they don't have packaging challenges. It becomes harder and harder to use wireline for communication using copper and other metals. So as you can see in this plot, approximately for every 30 dB more channel loss, we need 10 times more picojoule per bit because we need to do sophisticated equalization techniques, and we need ADCs to recover the data. So this has led, of course, in the past 10 years, with a huge amount of interest in using optical interconnects within the data centers because of the promise of low channel loss and the ability to cover longer distances with optical communication. So when you look at the power consumption in optical interconnects, it varies a lot, how much power is in photonics and how much power is in electronics. And it is possible sometimes that the power in the optical domain is more than the power in electrical domain and vice versa. So it means that really it depends how you design them. And also it means that optical devices matter significantly, and we really need to have very efficient optical devices and very energy efficient and high-speed electronics. So silicon photonics has been a promising platform for co-designing electronics and photonics and integrate silicon photonics with standard CMOS technologies in a hybrid integration manner. And they promise to provide low cost and power efficiency and also wavelengths multiplexing and achieving more than 100 gigabit per second per lambda. So in my group, we have worked both on design of receivers and transmitters using silicon photonics and standard CMOS, and trying to bring them together and design them together to achieve high performance. Today, mainly, I will focus on the transmitter design, which is actually a more complex problem because of the many parameters that we need to optimize together. So our major design objectives are to co-design optical modulators and electronic drivers and achieve close integration of optics and electronics and have robust packaging and improve energy efficiency and bandwidth efficiency with higher order modulation. So as we will discuss later, just NRZ modulation hits the wall in terms of speed for a lot of optical devices in silicon photonic platform. So we need to do PAM4 modulation or other type of modulation like QAM16 to achieve higher data rates with a given bandwidth of optical devices. So when you look at the optical modulators, we have a number of ways of building an optical modulator. And there are different parameters that an optical modulator can actually modulate. So a lot of modulators are based on phase modulation or PM, but also we have modulators that modulate the amplitude, and there are modulators that modulate both phase and amplitude. And actually, in the case of PM AM, you always get a little bit extra AM or a little bit extra PM. As I mentioned, the reason that design of the transmitter is a lot more interesting is that there are a lot of parameters that you need to work with and look at the trade-offs based on the overall performance that you are targeting to achieve. The optical insertion loss, the optical bandwidth, the voltage efficiency, meaning that, for instance, for a phase modulator, if you want a pi of phase shift, how much voltage per length of the modulator you need, or if it's an amplitude modulator, what is the absorption coefficient of the modulator. And then there are a lot of variations that we need to deal with in terms of temperature and process variations. So let me give you quick examples and kind of what kind of pros and cons each of these have. So in silicon photonics, we can perform phase modulation by having a PN junction that has carrier injection or carrier depletion mechanism. Or we can perform phase modulation using an MOS structure, as I will describe today. The good thing is that they can be used for both PAM, PAM4, or NRZ, and also coherent applications. But they have disadvantage of sometimes large parasitics, as we will see soon, and also the fact that you get some amplitude modulation as well. So now, if you have a phase modulator, how do you perform the actual transmission or creating an optical transmitter. So then you have to build an optical circuit using this phase modulation scheme. You can build a Mach-Zehnder structure or optical circuit, and you will have your phase modulators and drivers to create PAM4 or QAM output. Or you can create a resonant tank, and in that case, you need a much smaller, hopefully, a modulator to perform modulation. And these are called the ring resonances or micro ring modulators. So in my group, we have worked on both cases, and the good thing about ring resonators are they can be very small, very low power, but they suffer a lot from temperature variations and process variation. On the other hand, you can also build amplitude modulators, and these are usually electroabsorption modulator based on quantum confined Stark effect. And they are very suitable for PAM, amplitude modulation, or intensity modulation, and very difficult to use for coherent modulation. But today we will see that how we can use amplitude modulators to actually build coherent modulation as well. They are very small also, and usually they, if they're designed well, require low voltage, but sometimes they have high insertion loss, chirp, and nonlinearity. Nonlinearity makes them difficult, if there are nonlinearities, to create uniform PAM4 eyes, and you need to do extra work to make sure that you combat the nonlinearity of these devices to generate uniform eyes in a PAM4 transmission. So with this brief introduction, let me talk about about one example of using MOSCAPs for building PAM4 optical transmitters. As you can imagine from the name, a MOSCAP is very similar to an MOS device. We have a metal oxide silicon capacitor phase modulator that uses carrier accumulation to create phase modulation or a delta phi. So usually this structure is integrated with an optical waveguide to form optical confinement. This slide maybe shows this better for a silicon photonic type MOSCAP modulator, an example that you see here by creating this SiO2 slot that is very, very thin, and a very strong field can be generated here, and a large amount of carriers can be accumulated at the surface. It can be horizontal or vertical, depending how the waveguide is built and how this device is fabricated. So the nice thing about this device, compared to a simple PN junction, is that it has a very high optical modulation efficiency. The problem with PN junction that people use usually in a Mach-Zehnder architecture is that they usually end up to be very long to achieve enough phase shift. This device instead can be very small in terms of its length of less than 400 micron, which is very attractive because you can treat this like a lump device instead of a case of a Mach-Zehnder with a PN junction, which will require a transmission line type of driver, and you need termination and very high power consumption. But the problem, obviously, when you have this very thin oxide level and you have a device like this that is similar to an MOS, but it's 400 micron, as IC designers, I'm sure you immediately guess that this device will have a very high capacitance. So then now we have a situation that we have a very efficient device that can modulate the light, however, presents a very large capacitive parasitic to the driver circuitry, the electronics that need to drive this modulator with at least 1 volt. So this is the MOSCAP structure model, but as you can see, it's dominated by the CMOS, which is about 1.5 femtofarad per micron. So here is where you can actually use this co-design strategy to achieve data rates that are way above the bandwidth, apparent bandwidth of this MOSCAP device with large capacitor. So we are taking some strategies, and we designed our 28 nanometer CMOS chip and this silicon photonic chip together, and we co-optimize them. At the photonic IC, we use push-pull MZM to increase optical efficiency. We also wrapped the device around so that we can reduce the length of the electrodes that are driving this, the electrode that drives our modulator. Again, at hundreds of gigabit per second, you really need to keep this length under 200 micron or so to be able to avoid having termination and reflections. So a U-shape approach was used to really reduce the electrode length. And we tried to actually push the problem more into the electronics IC and use pre-distortion techniques and bandwidth extension techniques to compensate the big capacitance that we see from this modulator. We also realized that because this is a large capacitor, we absolutely cannot use wire bond. So as I show, we flip chip bonded the electronics and photonics. We 3D integrated them very effectively to reduce the parasitics. And also, we reduced the output swing below VDD to reduce the electrical power. So I'm going to show you this overall architecture of this device. We are trying to create a PAM4 modulation scheme using a Mach-Zehnder structure. So we're using a push-pull MZM. Basically, when one side is going up here, the other side is going down. And we are performing instead of having a DAC in the electronics domain and having a single modulator here, we have two modulators with two different lengths to implement LSB and MSB, and we drive them separately with the electronics. So the LSB MOSCAP will have around 500 femtofarad of cap, and the MSB has twice as more of 1 picofarad of capacitance. So then in this, we also have these thermal phase shifters that can be adjusted. So you can imagine that on top, we are generating these vectors in the field, and in the bottom, we're also creating the opposite for each bit of MSB and LSB. And when we combine them with this optical combiner, you basically get the PAM4 modulation. So on the electronics domain, it means that we have our data stream, we need to do serialization and then drive MSB and LSB designed separately, optimized for each of the modulators. And this is the way that we construct the device. Here is the PIC, and the EIC is flip chip bonded. Then the PIC is wire bonded to a PCB, and there is a thermal control under it. And this is just a photograph of the two chips on top of each other, flip chip bonded, one in 28 nanometer CMOS, and the other one is the photonic device in collaboration with Southampton University. So here is the two-channel CMOS driver in 28 nanometer CMOS. So at high data rates, of course, there are a lot of challenges in every block, including the serialization, the creation of the short pulses, as I will describe soon, and finally building the drivers to drive the MSB and LSB. So let's take a look at how we try to compensate for the large capacitor of the modulator. This is the LSB driver. So first of all, we have this T-coil peaking. We have small on-chip inductors that are designed and optimized for the load capacitor in a T-coil structure. This is overall a CML type of driver. As you can see, there are cross-coupled capacitors to enhance the bandwidth further. And then these resistors here are also reconfigurable because we have a lot of variation in the load. But in addition to that, we have this part, this extra current driver that is shown in this pink area. So effectively, here we generate short pulses that we inject into the output that looks like a pre-distortion. So we receive the data, we delay it a little bit, and then we combine the two data to create these programmable short pulses that will be added to the main CML driver to create sharp edges and enhance the bandwidth and our eye diagram. Okay, so I'm sorry. This is also our MSB driver. In our MSB driver that needs to drive a larger capacitor, our pulse generator is even stronger because it's very effective in helping us with charging the capacitor very quickly. And then we also have this differential shunt peaking. You see the inductor on top to further help us with driving the 1 picofarad load at least 50 gigahertz. So as I mentioned before, every single stage needs to have bandwidth extension, and we have used active peaking even in the serializer and CMO to CMOS conversion in the data path prior to MSB driver and LSB driver. It's also very challenging to create those short pulses precisely on chip. So we generate the delays in a very fine delay controlled manner that can be programmed off chip to control the duration of the short pulses that we inject into the capacitor. So these current pulses have adjustable widths of 2 picosecond, 4 picosecond, and 6 picosecond. So this is the CMOS chip in 28 nanometer technology. As you can see, these are the pads on the top. And this chip is then flip chip bonded to the photonic chip. These are the grating couplers. I hope you can see them. The optical input, optical output, optical input. And the low data rate signals are fed into the PIC, then they go to EIC, and then we perform serialization to combine the lower data rates and achieve high data rates to drive the MOSCAP. So here we show that the MOSCAP actually has very limited bandwidth. If you just look at the electro-optical bandwidths of the MOSCAP, they have the larger one has only 16 gigahertz of bandwidth, and the smaller one has, or LSP has 23 gigahertz of bandwidth. This is when we just simply use a 65 gigahertz 50 ohm terminated probe. So these are significantly below the bandwidth of 50 gigabit per second modulation for 100 gigabit per second PAM4. So here is our test setup. In the interest of time, let me go quickly. So here is our results of the output I in the two cases of not using any of our bandwidth correction techniques and peaking. So the first one, as you can see, is just a 50 gigabit NRZ. And with our bandwidth extension techniques, we significantly open the eye. And this side, on the right side, you see the 100 gigabit per second optical PAM4 without using bandwidth extension. And then the eye below shows our results with the bandwidth extension and compensating in electrical domain. So here is, again, another way of looking at the eye. If at the receiver side FFE is used, you see that this is how we program our optical oscilloscope to have 5-tap FFE to look at TDEC. And you see very nice open eye, and the same for a PAM4 modulation scheme. So overall, this transmitter achieves 2.4 picojoule per bit of energy efficiency in 28 nanometer CMOS. Of course, if we use this in a more advanced technology, the power consumption hopefully will go down. And this shows the power breakdown that, as you can see, a lot of power just goes into the buffering and pre-distortion, and then the front end MSB and LSB itself. So now that we talked about PAM4, let me see, there is. Oh, okay, so there is a good question. Which foundries made EIC and PIC? EIC was fabricated by TSMC, and PIC was fabricated by our collaborators at University of Southampton in England. Thank you for the good question. So yeah, feel free to send me questions via chat. Of course, at the end, we will also have a Q&A session. So let's now switch gear and talk about a COM16 transmitter using electro-absorption modulators. So far we talked about using phase modulators, building an intensity modulation scheme or PAM4. Now we are using an intensity modulation type of modulator for a coherent transmitter. So coherent transmitters have gained significant interest in the past 5 years, even for data centers. I'm sure you all know that coherent transmission are standards for long-haul communication because of robustness that they provide and the fact that we can actually correct for chromatic dispersions at the long distances. But with data centers now reaching beyond 2 kilometers with hundreds of gigabit per second per lambda demand, coherent transmission has gained a lot of interest to be used in data centers. I have to say that right now in data centers, intensity modulation are used, PAM4 and NRZ, but there are a lot of interest and a lot of research to use coherent modulation and transmission in even data centers. And as you can imagine, if we can use COM16, effectively we are sending 4 bits. So bandwidth of the optical devices also, bandwidth limitation of optical devices can be another motivation to use higher order modulation and achieve higher data rate. So electro-absorption modulators usually operate based on Franz-Keldysh effect, FK effect, or quantum confined Stark effect, where you have a lot of layers that create quantum wells, and by applying an electrical field, the absorption changes significantly, and you can perform modulation. So these devices can have high absorption coefficients, and they can be very small. But unfortunately, a lot of times they're nonlinear. And another problem is that they have sometimes relatively high insertion loss. So you have seen already that phase modulators can be used in a Mach-Zehnder structure for coherent modulation, actually, as I showed before. So you can build these Mach-Zehnder structures for I and Q, and then you do this polarity beam combiners to create the modulation scheme or the constellation that you are looking for. Here we are proposing to use the electro-absorption modulators in this parallel structure. More think of it as a parallel structure than an MZM structure here, to be able to create the constellation that we discussed and achieve QAM16. So as you can see, we can have phase shifters of 0, 180, 90, and 270 degree. And we can have these electroabsorption modulators that we just run them like on-off keying, similar to the PAM4. But here we will have 4 arms, and as we will see, we show that you actually need another arm in the middle to create a centralized constellation. But the challenge is here, another challenge is that you need unbalanced splitters because P1 and P up to P4 and the P5 in the middle are not equal. But all of these EAMs will be similar. And there is a challenge here that as you make your EM longer, the benefit is that you get better extinction ratio and your constellation size increases, but your insertion loss also increases. So it's very important how you optimize and design the lengths of your electroabsorption modulator. So as you can imagine, each of these would look like a PAM4. Each couple of these branches, if you look at the 2 top, will give you something like a PAM4. But unfortunately, EAMs always, in addition to amplitude modulation, give you some phase modulation as well. So in this case, about minus 14 degrees. So therefore, your constellation is going to be a little bit tilted and also shifted. Now, let's look at the lower part with 90 degree and 270 degree phase shift. So similarly, you get a PAM4 in this direction. That is also has a phase shift of 14 degrees. So if you put these two together, you get a constellation that is shown here in gray. And then if you add the middle branch and you design it correctly with the right amplitude and phase, you can bring the constellation back to the middle, which is usually at the receiver side is preferred to have a constellation that is centered at 0, 0. But it all depends on how you build and how much complexity you want to transfer to the receiver side. So one of the challenges is to build this unbalanced 1x5 splitter. This is more of a photonic design challenge in the silicon photonic platform. This was in collaboration with Rockley Photonics, and we used their silicon photonic platform. So here we need to create P, 2P, KP, 2P, and P from the input. So, and we have done the calculations that the K needs to be around 0.78 in this case. So the input, assume it's 7P, around 7P, and you get P, 2P, KP, 2P, and P. So that the way that we build it, we built this MMI, multi-mode interferometer combiner and splitter, or coupler and splitter. And we basically can generate pi at the output of this 1x7. And then we use another MMI here to combine 2 of them and create around 2 pi. And then the middle one, we build a custom 1x2 MMI to create k pi. And then similarly at the, as it's shown below. But for this MMI to create exactly 2p, you need different phase shifts in each arm in order to achieve 2p. So the way that we do it, we generate this phase matching or create the proper phase in each branch by designing the waveguide correctly after a lot of simulation and optimization, so that at the output you get exactly 2 pi. I'm sorry, you have to create phase matching. If you don't do phase matching, you don't get 2 pi, and you can achieve phase matching by creating waveguides that compensate for the phase mismatch that this 1/7 MMI creates. So this is what we did, and here are some of our simulations. First of all, to create this balanced 1/7 MMI. And then also, as I showed before, we need another custom 1/2 MMI to create kpi and 1 minus kpi, which you're not going to use it. So to do that, you have to create an unbalanced MMI that you can do that by creating a geometry that is not symmetric. Basically, we are cutting a piece of the waveguide here where we have multi-mode so that we can direct more light into one of the branches. So this was done. As you can see, this is the PIC design. And it shows the 4 EAMs and the middle branch, and each of them also have phase shifters. These are thermal phase shifters. So there were a lot of challenges here after we built it. So if anybody wants to build anything like this that has different thermal phase shifters, you should always be careful about the thermal interferences from one phase shifter to another phase shifter. So that's why we put them kind of far apart. But more importantly, the effect of the thermal phase shifter on the EAM performance itself. So these are very important considerations because most optical devices have some temperature dependency. The good thing is that EAMs have less temperature dependencies compared to, for instance, ring resonators, but still we saw some impact of the phase shifter on the EAMs. So here are the results of our QAM16 constellation. The first one, this is a 40 gigabaud, which gives 160 gigabit per second. And it shows that we had the ability to move the constellation using the fifth arm in the middle effectively to 0. And here we show our 200 gigabit per second constellation, again moving the eye from off center to center. But unfortunately, as you can see, we lost some SNR as we moved the eye from off center to the center. We noticed that if we build actually this device by playing with the phase shifters, we can actually create a hexagonal QAM16 constellation to achieve better SNR. And as you can see, this is our 160 gigabit per second hexagonal QAM16. And this is our 200 gigabit per second hexagonal QAM16. Let me see. So the question is that what is the link distance for this constellation? This is a good question. I don't remember exactly. We tried to, so it's not very high, but we used a relatively long fibers to go from the transmitter to the optical analyzer. But I don't have the number in hand exactly. But it wasn't definitely 2 kilometers. We used a long fiber to mimic some distance. All right. So now let me summarize here with this 5-arm QAM16 architecture. We were able to build a QAM16 transmission at 200 gigabit per second, which improved our speed significantly, achieved high data rate using this kind of EAM. So this is, again, kind of a non-intuitive way of building QAM16 using amplitude modulators instead of phase modulators, but amplitude modulators are very robust against process variation and are much more compact compared to phase modulators. So now, because we do have actually time, maybe for 10 minutes, I completely switch gear here and talk to you about another area that really co-design of electronics and photonics can help us reduce power consumption, reduce the size and the cost of our devices. So in my group, we also work a lot on biomedical applications, and there is a huge interest in portable and wearable biosensors today. And there are many mechanisms for biosensing. We can use tear, swab, saliva, sweat. We can have interstitial fluid. We can use this interstitial fluid or urine. So there are different mechanisms of sensing. And then the bioelements that we can use for sensing are antibodies, nucleic acids, cells, or proteins. So one very interesting ways of performing biosensing is to use bacteria and genetically modify them with fluorescence proteins that they can basically help us to sense changes in the environment around them, or sense the presence of a target molecule, or differences between similar compounds. Basically, an external agent or another compounds can trigger gene expression. And for instance, the generation of the fluorescence proteins that would fluoresce, and we can sense whether a certain biomarker is present or not. And then we can encode cells with certain DNA sequences so that we can also enable production of enzymes, nucleic acids, and molecules, and in fact create a two-way control system that we can use fluorescence sensing for sensing of certain biomarkers, and then use light to trigger gene expression and basically generation of certain enzymes or molecules that we want to deliver, for instance, in an ingestible capsule or in the environment. So for this, it means that we need a two-way communication between CMOS chips or electronics and biological cells. So in this project, our goal has been to create this two-way communication between biology and electronics. So fluorescence detection is actually a very established mechanism in biology, and it works very well. It's based on excitation at this excitation frequency or wavelengths, and then we will have a Stokes shift and a fluorescence signal that is at a slightly different wavelengths. And then if we use an optical filter, we basically can separate the excitation and fluorescence and detect the fluorescence light. So I'm going very fast here because I know we don't have much time. So traditional fluorescence sensors are very, very bulky. I'm sure you have seen some of them. It's a big box instrument in the lab. It's not something portable or implantable or wearable. So they require expensive optics, but they have very high sensitivity, and they can measure the fluorescence at different wavelengths very precisely. So our goal here, in order to build a tiny device that can be used for environmental sensing to detect, for instance, hazards in the environment, such as arsenic, or to use it in a drug delivery system in a control loop, we want this device to be extremely small and also very low cost. For instance, you want to spread all of these sensors in the environment to detect the hazardous material. It should be very, very low cost. And in fact, this project was funded by the Army with the initial goal of detecting arsenic in the environment. So CMOS technology would allow us to make the device very small, very low power. And we also want to have continuous real-time monitoring. So our goal is to build everything, including optical elements of this fluorescence sensing on a single CMOS chip. So it means that we have to build the optical filters to remove the excitation light using structures in a standard CMOS. the photodetectors, and also all the electronics to detect the tiny, tiny current that is generated by the on-chip photodetector. So one of the biggest challenges is actually to build this optical filter on chip. We basically need to build this bandpass filter, and we actually use the existing metal and dielectric layers in CMOS using plasmonic effect with this metal structures, and building resonators, guided mode resonators and cavity mode resonators to guide the light only at a specific wavelengths from the surface of the chip all the way to the photodetectors. So I'm not going to go through all the details, but we basically built this this kind of cavity structures, plasmonic cavity structures that kind of looks like a coaxial design, but the center of it has a tiny amount of layer of metal. And the challenge here is that we have to comply with the DRC and satisfy the DRC while creating this kind of filters. Another major challenge is that because the light comes in from all different directions and also with both polarities, the design should be polarity insensitive and also angle of arrival insensitive. So as you can see, we finally, after looking at many different structures, we designed these structures using metal layers, and we showed that we basically have relatively good at resonance. For instance, you look at our TE and TM, both are transmitting, and off resonance, both are blocking. So basically, we look at the response to polarization for the TE and TM, and also we have to look at the response with the angle of arrival. As you can see, up to about 15 degrees or so, we have good performance in terms of angle of arrival. So we also needed to build the photodetectors using the existing layers. So one thing that we did is that we used different PN junctions that are available in the MOS technology to basically create another bandpass filter using the photodetector itself and further filter out the excitation light. So I talked briefly about optical filter design and silicon photodetectors. Very quickly, I would like to talk to you about the electronics as well. So it is indeed at the end, because our filters are designed by using very lossy copper metal layers, our filters are not perfect. So we need to, and the excitation light is significantly higher than the emission light. So we needed to also to work on the electronics domain to remove the remaining excitation light and also the background light. So as we will see soon, this chip has ability to have 3 different wells on top, because we want to detect actually 2 different fluorescence proteins, A and B, at different wavelengths. And then we have one center well that has the same type of cells, the same bacterial cell, without the fluorescence protein. So this well acts as a reference well for us, and we created this differential structure to further remove the effect of the excitation light that you see comes from the side, exciting the cells to fluoresce. So we are talking about tens of femtoamps of current that we need to detect. So a lot of work went into, and also we need all these switches to measure different wells. So a lot of work went into creating low leakage switches and creating very low noise differential capacitive transimpedance amplifier with variable gain. And then we use, again, another way of filtering using a correlated double sampling to remove the low frequency noise and offset. So this is the most colorful chip that we have ever built in my group. And the reason is that we have used all this top layer, the metal layers, to create different types of filters at different wavelengths. So therefore, you see the reflected light back, and the chip is very, very colorful. So it's very small. It's 1.5 millimeter by 2 millimeter. We can measure optical density, and we can measure two different fluorescence proteins. It is designed to, we also designed these microfluidic chambers that sit right on top of the chip. So this project brings biology, microfluid, optics, and electronics all together, very challenging. And we showed that with this tiny chip, we can actually measure the presence of two different fluorescence proteins in a single mixture. So one of them responds to LED1, one of them responds to green LED, and the other one responds to a red LED. And then each of them fluoresce at a slightly different wavelengths. And we can measure them by turning on LED1 and LED2. As you can see with LED1, LLS orange is excited, and with LED2, the M-cherry fluorescence protein. As I mentioned, our goal has been to create a two-way communication system. This is my last slide. So here we showed that with one light, for instance, here, look at this, we can, with red light, we can turn off cell growth. And with green light, we can enable cell growth and fluorescence protein production, and we can measure over time. So the green shows that the production is enabled with green light. The red shows that the fluorescent production is disabled with red light. So this is the first CMOS chip that has measured dynamic cell growth in real time. So I'm going to stop here. My main message in this presentation is that electronic-photonic co-design with deep understanding of both photonics and electronics can really help us solve difficult problems from high data rate, energy efficient communication systems to miniaturized low-cost biosensors. So I would like to stop here and answer any questions you may have.
Thank you, Asita. Very impressive results. Very good work. Thank you so much. We have some questions in the chat, but before we go into the chat, is there any questions from the audience here? If we have questions, we could ask.
Hello?
Yes,
Hello?
we can hear it.
Can you hear me?
Yes, but if you speak a little louder, that would be great.
Thank you, Professor Mami, for the presentation. I hope you can hear me good. So my first question is regarding the chirp effect in the coherent modulator, and if you've seen characterize it and the chirp performance.
That's a great question. Yes, the EAM does have some chirp that we have tried to minimize it, and we have characterized it. So part of the performance degradation that you saw in our eye diagram is due to the chirp. I think it is discussed in our paper. If you look at the OFC paper that we had 2 years ago, I don't have the exact number in my ready, but it is correct that EAMs do have chirp, and that has been one of the challenges in our design.
And I'm assuming it would be higher than the traditional MZMs, right? The chirp in EAMs.
That's a good question. Yes, compared to just the PN-based modulator, these EAM devices have higher chirp.
Thank you. Next question. I just have one more question. The EIC and PIC, how did you flip chip them? Did you do it in-house or you sent it outside? And if you could share with us because it looks very clean and like great done.
Yes, the flip chip bonding was done by our collaborator at the University of Southampton. Yeah,
Perfect.
they did, but for them also has taken years actually to get to this point. So they have been working on their technology for quite some time.
Thank you, appreciate it. Thank you.
Any other questions? Okay, before we can go into the questions from the chat, Mohammed Saad is asking, how do we minimize crosstalk in the coherent transceiver modulators?
Sorry, I did not hear you very well, Ajay.
Oh, the question Mohammed Saad is asking is, how do we minimize crosstalk in the coherent transceiver modulators?
That's a great question. So in terms of, let me maybe go back. Find the proper slide here. So first, let me clarify if you're talking, I assume you're talking about the crosstalk in electrical domain.
Excuse me, can you hear me?
Yes.
Yes.
Yeah, it's just regarding when you said there could be like temperature leakage
Yes.
due to the optical or like thermo-optic phase shifters. So like if we're building an IQ MZM, we'll have many thermo-optical phase shifters. So how can we make sure this thermal control doesn't leak into each other?
Yeah, as I mentioned, we did see that. So people have looked at this problem. First of all, you need to see how much real estate you have in terms of the separation that you can create. And then and then also initially during the simulations, it would be best to include some thermal simulations before the chip fabrication in terms of effect of the phase shifters. Other option on the fabrication side is to create some isolation between the EAM and the phase shifters by removal of the substrate locally around the EAM to create some thermal isolation. But overall, it's a challenging problem, and I think the best way is to include the effect of the phase shifter in the initial design of the whole system.
And
that's something that we realized later on that we needed to do, because in our case, we thought that just by separating them, we will get enough isolation, which was not the case. And we did see some effect on our EAM when we used our, when we had to adjust our phase shifter.
Thank you. You mentioned that like raising resonators are very sensitive to temperature,
Yes.
but like are MZMs also like sensitive to temperature, or this can be neglected?
So MZM, so keep in mind, MZM is the circuit structure. So that's MZMs, for instance, this is an example of MZM being, and depends what kind of modulator you put in your MZM and how much. For instance, our MOSCAP is not very temperature sensitive. So while MZM is a structure, what you put as a phase modulator or amplitude modulator in each arm at the end gives you the thermal sensitivity that you have. So for instance, this is one example of our MZM being sensitive to thermal effect of our phase shifter. But there are a lot less sensitive in the overall temperature variation in your system. I don't know if that's clear, because ring resonators are extremely sensitive to temperature. because we are actually operating them at the resonance. And any system at resonance is very sensitive to changes because we have a very sharp response. But not these kind of devices in MZM do not have such sensitivity. They have much smaller sensitivity, but of course it's not zero.
That was clear. Thanks.
Thank you. We have one more question, but we have one past 1 minute. So we have one more question, which is what is the distance for the link distance for the constellation? That's your slide number 60 of this.
I think that question, I already answered it. Is it the distance?
Oh, you already answered.
Yes.
Okay. Yeah. Okay. Thank you, Sita. Thank you so very much. So now the next week's presentation would be made by Professor Mike Chen from USC, and let's all meet next week. Thank you all.
Thank you so much.
Thank you, Asita. Thank you once again.
Bye-bye.